Hello, and welcome to today's Saratech enablement session. My name is Andrea Hall, and I'm the Customer Relationship Manager here at Saratech, and I'll be your host today. Presenting today, we have Dan Nadeau, and he is an applications engineer here at Saratech, and he's going to be talking to you about basic nonlinear analysis, Solution 106 in Simcenter. And with that, we do have a special treat today. Before we go over to Dan, I'd like to introduce Ken Sherwinski. He is the Senior VP of Engineering Services here at Saratech. He has over 30 years of experience in the engineering sector, and he has lots of great stories. So I just asked him to come on and share a little bit of information about Saratech services. We do over 100 projects each year, and a lot of them are with repeat customers. So with that, I'm going to pass it over to Ken.
Andrea, thank you. I appreciate that. I'm not so sure it's a treat to have me on, but it's a pleasure to be here. I want to let everyone know here, I hope it's okay that I do about a 30-second Saratech Engineering Services commercial. It's really, Saratech has 3 business units: the software sales, 3D printing solutions, and engineering services. There's about 100 employees in the company, and over half of them are in the technical services group. The bottom line here is we just don't know software. We know core engineering capability. We have a lot of experience in structures, mechanisms, systems design and analysis, and we help a lot of customers solve a lot of complex and challenging engineering problems. Our customer list includes electric car vehicle manufacturers, space companies. We're a full offload work package technical supplier. We support the aerospace sector. We support the biomedical sector. We have a complex CE group that does a lot of nonlinear dynamic fatigue and crack growth and thermal analysis. We support optical systems. We do design and build of large and simple assembly and test tooling. And we do a lot of work in the electrical, hydraulic, pneumatic system integration for aircraft and other transportation type vehicles. This is the last slide. The bottom line here is that Saratech Engineering Services, as Andrea had mentioned, we do over about 100 projects a year with a lot of repeat customers. Everything we do is project managed. We start with the project plan. We take time to really understand the technical requirements, provide milestone deliverables, and get back deliverables to our customers within time, quality, and schedule. Thanks very much, Dan. Knock 'em dead with your presentation. Thanks, folks.
All right, thank you. Hello and welcome. My name is Dan Nadeau. I'm an application engineer here for Saratech. My primary focus is FEMAP, NX-CAE, which is now called Simcenter, NX-CAD, and NX-Nastran, which is now called Simcenter Nastran. So today, the agenda here is I'm just going to give you a brief introduction to nonlinear analysis, Nastran Solution 106. And including that, I'm going to talk about material nonlinearity, geometric nonlinearity. And to help, I guess, explain or show these, I'm going to go over a couple demo models, one on material nonlinearity, one on geometric nonlinearity, one on post-buckling, which will help show off some of that geometric nonlinearity. And then hopefully I can have enough time to go and show you a model that has both geometric and material nonlinearity. So most nonlinear analysis, most structures are actually nonlinear in reality when you're loading them, because the stiffness of the structure is changing as you're loading it. But most of the time, we just give a linear approximation, and we assume that's good. But it's important to understand when that's not good enough. So here are some implications of a linear analysis. So some of these things are useful, and some of these things, might be detrimental to your solution. So force is equal to the stiffness times the displacement. So the nice thing is, if you are in a linear realm, you can just scale superimposed loads instead of running different loads. So if you have a 1G load case, it's easy to scale that 1G load case into different G load cases in this case, instead of resolving the model. So stress is proportional to strain. Loads always maintain the original direction that they have been applied. Now, materials are not going to yield. We have small strains and small displacements. So here are some types of nonlinear behavior. You have geometric nonlinearity, so you have large displacements. You have material nonlinearity, so the material itself is yielding. Or you have follower forces. So by default, in a linear solution, the force always follows the same direction. But if you want to follow the load path of the structure or the direction of the structure, you can apply these follower forces. And then some other nonlinear behaviors are changes in boundary conditions. You can find information in the basic nonlinear user's guide, which can be found. I have a link here below. So when you are looking at documentation on this, I highly recommend going and looking at this guide. So the first thing is geometric nonlinearity. So it's problems that involve large rotations and large deformations. The most important thing is the model on the deformed shape of the structure appears distinct from the original geometry. You can turn on geometric nonlinearity with the large displacement parameter. So for a large displacement parameter, it is for small strain elements. The elements may undergo large total displacement and rotations, but the net deformation of each element has to remain small. Many real-world problems have stiffness that changes as geometry is loaded. So a simple example here is a yardstick under compression. As you push down on that yardstick, the load's going to change. So it's going to start out stiff, and as you keep on compressing it, at some point it's going to buckle, and then it's going to become less stiff. Inside Simcenter, there's a toggle right here for large displacements, LGDISP, and this is where you can, include or not include those large displacement effects. The other nonlinear effect that can happen is having nonlinear materials. So now we are going past the point of yield. So normally you have a linear slope, and it's going to continue in a linear realm. So the point here is now we want to figure out what happens after it has yielded. So to do this, there's a couple different material models that we're going to show and we're going to define. So the first one is a nonlinear elastic material. So the strain returns along the original curve. So whatever actually yielded. And then the other one is nonlinear elastoplastic, where you have reached a location where it has yielded, and then it's going to keep that residual strain inside the structure. So we've made it past the yield point, and we're doing stuff after that, and it is now going to permanently deform the structure. So to set those up inside Simcenter, this is the form, and we're going to go through this in a demo model. I think a demo is easier than me explaining it here. But inside here, these are the nonlinear material models that you can define. You can do nonlinear elastic, like I said. You can do elastoplastic. And defining the elastoplastic model, you can do that with a stress strain curve, or you can do it with stress and a plastic strain curve, or you can define H, which is a bilinear stress strain curve. Inside Simcenter, when you would go and create the solution, what I'm going to go through is solution 106. And I'm not going to spend time talking about 129, but that's also included in with the basic nonlinear package. The basic nonlinear package is included with a Nastran basic solution. If you want to use advanced nonlinear or the multi-step nonlinear 401, 402, you would have to have an add-on license. Now, an important thing, and this comes up a decent amount, if you have contact in your model, contact is not supported in basic nonlinear analysis. So defining nonlinear analysis. So these are the parameters that you have to set up, and it's under NL-PARM. So if you have questions about, what some of these options do, I highly recommend looking in the QRG and looking up the parameter NL-PARM. And the basic ones that you should understand if you are doing basic nonlinear analysis is you have the number of increments, which divide the total load, with the final being 100% of the load. You have an output flag. How often do you want output? So sometimes you don't want output all the time, but sometimes you just want to see it at the end. But maybe you want to see it, what happens at 20% of the load, 50%, et cetera, whatever you want out. Then there's options where you can specify the updates in the stiffness. Because this is an iterative process, the stiffness matrix does get updated. So you can control that a little more. And then the other option that you might want to adjust here is the maximum iterations per load increment. So maybe you're having issues, you need to give it more increments. That is where you would go ahead and you would edit that. There are some more advanced options, but for this webinar, I don't think we're going to discuss them. And like I said, if you want to change some of them, please look at this parameter NL parm. All right, so let's go into the software and let's cover some of these items. I think it's easier to see them in action. So for this, I'm going to use NX as the pre-post processor, and I created a simple model. It's just a flat plate, and we're just going to set it up, and we're going to look at, hey, what is the effect of geometric nonlinearity on this model? So for this, I'm going to create a new fem and sim, and I'm going to create an idealized part. In this case, I'm not going to use it, but it's by habit I would create it. So inside here, the first thing that I want to do is I'm going to solve a basic linear analysis. Give me a baseline. If you are doing nonlinear analysis, it's highly recommend that you start here. So let's go ahead and mesh this part. I like to use this lightning bolt. It gives an approximation of a size. Then I usually divide it in half. For this, I'll divide it in 4. For this case, it's going to go into an automatic mesh collector. It's up to you how you like to set this up for mesh collectors. You can create them on the fly or have them created ahead of time. What I'm going to do is I'll create it on the fly. I'm going to say this is my plate, and it is a P shell. And now I'm going to define the physical property. So for this case, I'm going to tell it it's 1/8 of an inch thick, and it's going to be made out of some material. In this case, I'm going to go ahead and use the library that already exists. And we're going to use 4340 steel in this case. So now I have my part meshed with my material and property. So it actually does have, a thickness due to it, and it is meshed with those 2D plate elements. So let's hop up to the sim level, and at the sim level is where we can apply our loads and constraints. So for this, I'm going to go ahead and apply a pressure to this entity. In this case, I'm going to enter a pressure of 20 pounds force per inch squared. And I'm going to just apply it to that surface. And I need to apply a constraint. I'm just going to apply a fixed constraint to the edge. We're just going to make this pretty simple. Now, inside Simcenter, it does have these filters. So I highly recommend using them. So in this case, I'm going to grab an edge. I could also grab the nodes on here if I wanted to, switch it to nodes. The nice thing about applying loads and constraints to geometry is that if I would change the mesh, my loads and constraints would stay there if that geometry still existed. So now I have my boundary conditions, my loads, materials, my properties. I can go ahead and set up the model to solve. So the first thing that I'm going to do is make sure I have my loads and constraints in my solution 101, solve it, and look at results. So this takes no time to solve. All right. So before I look at those results, what I want to do is I want to create a new solution. And this time I want to include that solution 106. Now there is an option to do global constraints and subcase constraints. It's up to you how you set up the model if you have global or subcase constraints. One of the nice things about running a solution 106 solution is that if you have multiple subcases, they are a continuation of the previous subcase. So where a 101 solution, it will zero back out, where a 106 solution is a continuation from the previous subcase. So in solution 106, under bulk data, this is where I can toggle on and off large displacement. So in this case, I care about the geometric nonlinearity. I want to see what effect I have when I push down on this plate due to the geometry itself causing stiffness changes. So under case control, this is where I would control my nonlinear parameters. So for this case, since it's a simple plate, I don't really need to change much. I can just give it, 1 increments. I could say break the load down into 10 pieces if I wanted to. I only need 25 iterations is plenty to solve this in no time. And then how often do you want output? In my case, just give it to me at the end because I only need 1 case and I just want to see what happens. But if some reason I want to see what happened at, a percentage of the load, I could see that if I wanted intermediate output. And right here is where I can change my stiffness update. So by default, I use automatic, but you can do iteration and you can do semi update as well. So for my case, I'm going to do auto. All right, so now I have that set up. I can edit, rename this so it stands out and I can see what's going on. And I'm going to go ahead and solve this solution. Once I make sure I have my boundary conditions and loads inside this solution. And we'll be able to compare the differences. So this takes, I don't know, a little bit longer since it is running a solution where it needs to update the stiffness matrix, but it has been completed. So now I can go ahead and post-process this information. So the first thing that I'm going to do is look at my solution 101, and we'll look at displacements in this case. Now, in this software, it's very easy to look at multiple solutions at once. So go ahead and plot both at the same time. And if you wanted to view these synchronous, you could go ahead and synchronize these together so that we can look at them. But what you can really tell here is the displacement on this one is much, much larger than the displacement on the one where I'm including the geometric nonlinearity. So this is a simple example that shows where geometric nonlinearity has a huge effect on the solution. So on the left is my regular solution 101, and on the right is my solution 106 with my parameter large displacement. If I didn't turn on that large displacement parameter, it would look identical to the model on the left. All right. So here is another simple model. It's just like a telephone tower, I guess, or some sort of 2D structure. Now I can look at, and it's made up of, I guess I can go to the FEM part and I can control the visibility on these entities so we can see what's going on. I guess edit display. And these have some sort of thickness to them. It's pretty thin, but it's a thin-walled beam type element here. All right. So I wanted to symbolize this thing buckled. So up at the top, there's a large load. In this case, it is a force, and that force has a value of 20,000 pounds. And then I have a constraint at the four corners. So what I want to see is this part buckling. So what I did was I set up a solution 105. A solution 105 is buckling with that load and constraint, and we can go ahead and solve that. I don't think I have results now. So I can go ahead and solve this solution. And this takes a moment to solve. And I can go ahead and post-process these results. So for buckling, you get one subcase, which is telling you the effect, and the other one is telling you at what value the structure has buckled. So in my case, it takes me 0.46% of the load to buckle the structure. So I can look at this and I know that, oh, well, that percentage is going to buckle the structure. So what I went ahead and did was I set up a nonlinear solution where I just want to push this thing through and see what happens after it has buckled. So I'm including this thing buckling out and I'm continuing to load it as it has buckled. All right. So I actually set up one without having the large displacement. And if you imagine you don't have large displacement, this thing's just going to continue to go down, go down, go down. It never buckles. So if you want to see it buckling, you need to make sure that you have that large displacement parameter turned on. I'm going to go ahead and solve that. And this takes a moment. This screen on my other running through.
And while that's going, just a reminder, if you have questions, you can type them into the questions box on the right-hand panel.
All right. So now this has solved, and we can go ahead and look at results. So if we remember from our first run at 0.46%, the structure buckles. So we can go ahead and look at, in this case, we'll look at displacements of the structure at subcase here. We got something normal. So if we start at subcase 0.4, it's just before it buckles, and we want to look at displacement. You see, we have 0.1 inches of displacement. So if I go step to the next is at 0.45, you notice this goes up to, half an inch. And this is telling me right after here is where it buckles. So if I go from 0.45 to 0.475, you'll see my displacement went up an inch and a quarter, basically. And you'll see that it continues to go drastically as I step past that point of buckling. And at some point, this solution failed because it couldn't converge. It just was way beyond buckling. So this is a case where maybe you wanted to look at results, or you want to create a graph across some sort of iterations. You could go ahead and see what happens. So if you want to see what happened from its start to, in my case, I'll just go a little after it buckled. And maybe I want to see for, this node, I can go ahead and graph that. And you can see at about, right here's that 0.45, this thing starts to take off. And that's what it's telling us based on here, that at some point this thing starts to buckle. And the nice thing about including these nonlinear effects is I can see what happened after it buckles, because maybe, I'm trying to figure out what's going on post-buckling. And this really shows the difference if you do have geometric nonlinearity on your model. All right, so next thing that I want to talk about is material nonlinearity. So the material itself has yielded. So I went ahead and used the atlas of stress strain curves to gather information about some materials here. So in this case, I looked up 4340 and 6061 aluminum and grabbed information and plotted it here in Excel so I could use it for demonstrations and things like that. So I went ahead, grabbed its stress strain curve, found where it yielded based on my curves, and I went ahead and created this. Now, inside Nastran, these two nonlinear material models exist. One is you are defining the information after it yields as a curve, as stress versus strain. You can actually do stress versus plastic strain if you have that information instead of strain, so you only have the plastic strain information. Both are available. And then you have one which uses a thing called the plasticity modulus, which is H, which is just a bilinear slope after it has yielded. So in this case, I calculated my plasticity modulus by just doing a rise over run. So I'm assuming after it yields to where it ends, it's just a linear slope. So we're breaking this down into another solution. So we have a linear solution, not a solution, another section of the curve. So we have a linear slope here, and then we have a bilinear, which is a second linear slope after it has yielded. So why would you choose one over the other? Well, bilinear slope is much easier because it's just a straight line and it does linear effects after it has yielded, a straight linear curve. Where the other one, you have all these extra points, and Nastran needs to do interpolations. Now it's up to you, how accurate you need your solution and what you want to use in that case. So here's just two quick examples, and I'll go ahead and show you how you would put this inside the software. So before I get there, I'm going to take this part. We're going to use it for our next example. So let's go ahead and create a new FEM and Sim, and we'll make sure we create our idealized part because I don't want to mesh this as a 3D part. We're going to go ahead and mid-plane it. All right. So normally I keep the solution 101. If I makes sense to start with a 101 or a eigenvalue solution, make sure your model is set up correct before you go on and go to the next step. So we'll leave it there as default. And let's go back to our idealized part. Now, anytime that you need to edit an idealized part, you must promote it. Once you promote this part, then you can make changes and bring it to your own level, and you will not adjust the bottom level assembly here. So in this one, I'm going to mid-surface this. I'm going to grab all these surfaces. And there's this button right here that automatically progressively mid-surfaces it. And it does a very good job. So it does have a little bit of gaps. Just like most mid-surfacing commands, we need to spend a little time fixing it up. So in this case, I'm just going to say extend sheet. I'm going to go ahead and grab a couple curves. And we're going to extend this to this face out here. Now, in my case, I'm just going to go ahead and grab the other edges, and I can do this all at once. And I'm just filling in this gap so that I get a nice, clean connection between one and the other. So now I got this part nice and mid-surfaced. I can go to the fem part. Lets me know that something has changed. And once I hide my original geometry, I'm left with these plate surfaces. So here, I'm going to stitch edges. I'm going to combine these edges together. This is what I would call non-manifolding. And when I do this, it's just combining those free edges. So right now there's two curves that share the same location, one from this piece and one from this piece. Now what this does is it combines them together so that they share that common edge. And now I can do something if I want to remove these, extra tabs or the stuff that I'm not using. I can just use a simple command like a delete face, and I can remove them from the model. Now, I guess a little tip and trick here is if you select something that you don't want, using NX, just anytime that you hold down the Shift key will unselect that selection. So I can just delete these parts from my model, and now I'm left with this nice piece that's nice and connected here. So managing materials. So once you hit this selection, you can do a local material, or you can use the library that already exists. If you want to use one of these and make it your own, you can just right click on this and say copy, and that will bring it into your local materials. So in my case, I'm going to create my own material, but I'll just do this for an example. So you could right click copy, and then you could edit and make any changes that you wanted. So in this case, you start with 6061, and I had my 6061 already defined, and I want to include my non-linearity here. Let me open that. I can go ahead and it's going to yield at 38 KSI, so I know that. So that's good. So inside here, this is where you have your stress strain related property values. So right here is you could enter in a stress strain or H. So you could enter in the plasticity modules right here. If you didn't want to enter the plasticity modules, you want to do a stress strain curve, you can hit this equal sign and you can go to a tabular field. Because in this case, I already have a tabular field. I'm going to put it on my other screen so I can copy and paste it. And you can say it is strain versus stress, and you can just edit it in a table. It'll pop open Excel for me. And now I can paste my values from my other screen into here. All right.
Hey, Dan, when you're done with this part, we do have a question.
Okay, go ahead.
When running a nonlinear FEM, it seems like you'd always want to enable LGDISP. Is there a good example of when you do not want to enable that?
So a good example would be if you are having issues with your model converging and it wouldn't work and you're having issues, you can toggle it off to not include the large displacement, and it should help it converge because it doesn't have to deal with the geometric nonlinearity. But most of the time, the reason why you are in here is because you want to toggle that on. But maybe you just want to make sure that your material nonlinear model that we're working on right now works. You can toggle that one off and you can, use it for troubleshooting. So here I just copied and pasted that stress strain curve into here. So now it exists. And if I wanted to, I could go ahead and plot that and look at it and make sure that is, how it was in my other model. So that's how we could enter in a stress strain curve. Now, important thing is you need to tell it where it is going to yield. So in this case, it was 38 KSI. Now I need to make sure that this value matches this value right here. If it does not, Nastran will yell at me. Actually, I don't think it will solve it. So to define nonlinear material models, you need to enter in the stress strain curve or the plasticity modulus here. You need to tell it where it yields. Now, here is the type of nonlinearity. So in this case, it is nonlinear elastoplastic. So this thing is plastic. If you don't want it to become plastic and keep residual information, you would type in nonlinear elastic. That way, it would follow the stress strain curve, but it would not permanently yield the structure. Now, if you have plastic strain information instead of total strain, you would just change this parameter right here. So defining the material models isn't super difficult. You just need to make sure that you have the right parameters. Now, for this example that I'm working on, I'm going to create a new material. And I'm going to go ahead and call this isotropic material. So this is just the normal material that I'm going to work with. So this has a 2.69 e to the 7, and it has a Poisson's ratio of 0.3. Now I'm going to make another copy of this, and I'm going to use this same material so I can copy it. And this time I'm just going to say this one's with an H value. And now I'm going to go ahead and give it an H value. In this case, I calculated it, 517,571. And this model yielded at a value of 34,970. Now, just because I went through this, we'll go through this one more time. And this time, instead of using the H value, I'm going to go ahead and enter in a tabular information. I'll copy it. I'm doing it on my other screen. So I have stress versus strain again. And it'll pop this open. Copy. There we go. And there's my values. You need to make sure that your stress and strain value match where you tell it's going to yield. And once this closes down, it should be in here. All right. So inside here, this is not H, so this is a stress strain curve, SSC. All right. And now it yields at the same location, except this time we're using this stress strain curve, and we can plot it if we wanted to. So this model, I created 3 materials. Well, I guess this one, but I didn't really use that. But for this one, I have a linear material, a nonlinear material using H, and a nonlinear material using the stress strain curve. So now if I want to go ahead and mesh this, I can create my collector. So I'll create my collector ahead of time. It's going to be a 2D. It's going to be a P shell, thin shell, P shell. This is my USB case. And it is referenced to any material that I wanted. So in this case, I'm going to start with the linear material. It has a thickness value. I don't remember it, so I'm going to leave it blank now. And now I'm going to go ahead and 2D mesh the structure. So like I said before, grab the entities, use the little lightning bolt, and I usually like to go in half, and then make sure it's going in the collector that you want. If you want to change any of these mesh properties, you can go ahead and change them. So now I have my structure meshed. What I like to do if I do mid-surface geometry, I like to right-click on the mesh, and I will say Edit Mesh Associative Data, and it will get its thickness from the mid-surface it created. So then if I go back and I edit anything with the geometry, it will automatically update the mesh with the new thickness or whatever value that was on that original piece of geometry. So instead of me defining the property to have a thickness, I reference it back to the original geometry. One of the disadvantages, you must have the geometry open. But one of the advantages, if somebody makes a change, it's automatically going to propagate and you don't have to worry about it on your end. So now that I have this meshed, go to the sim level where I can apply my constraints. So this, I'm just going to do a simple pressure on this top face. And I'm just assuming somebody's standing on this USB case. So I'm going to have a pressure here. It's going to be pretty straightforward. And I'm just going to fix the bottom. Now, in my case, my constraint, I need to change this to polygon face. And now I went ahead and fixed this bottom. So now I have my entities set up. I can go ahead and solve a linear solution. So go ahead, solve. And now I have my load to my constraints in my linear solution. And it went ahead and finished. And we can go ahead and look at results for this. So now we didn't really care about the nonlinear effects of this thing. So if we look at our stress values, I told this thing when we defined our nonlinear materials, it actually yields at, I think I said 35 KSI. So this thing's way past yield. So if we wanted to include that information, we could create a new solution. And in this case, it's going to be solution 106. we want to make sure that we toggle on large displacements. And in this case, we can enter in our parameters. So maybe I want to break it down in 10 increments of the load. I could do that. If I wanted to do that and I want output at different locations, like the buckling, I said, yes, I want output at multiple locations because I want to see what happens as it's buckling. In this case, I just want to see what happens after the load has been applied. And you can break down this load into more increments. If you're having issue solving, try to give it more increments or more iterations per increment. In my case, this is pretty straightforward, so it's not too bad. So now, if I want to include the material nonlinearity, I need to make sure that when I go back to my FEM part and I look at my property, I need to make sure that I grab my material. In this case, I'm just going to use one, just looks like we're running low on time. So I'm going to use that H value, go ahead and go back to my sim. Now this one is my solution 106. I'll make sure I label it so we can see it. And this is including geometric and material nonlinearity in the same solution. And this will take a moment to solve. And I don't know if I'll have enough time to show you these convergence charts as it goes through its iterations of the stiffness matrix. And there we go, we got to our solution, and you'll notice that my solution will take much longer because it does have these iterations. And now we can look at these results, and these results are going to be different if we look at something like our stress value, because the difference between one and the other, where this one I told it yielded at 35,000 psi, where this one just stayed on a linear slope throughout the solution. So hopefully I got you guys up to speed and at least an introduction to nonlinear analysis using Simcenter 3D here, and introduced you to the solution 106. I talked about material nonlinearity, geometric nonlinearity, and I went through a couple of those demo models. Thank you guys for your time. If you guys have any questions, feel free to let me know. You can reach out to me afterwards. My email is dnadeau@saratech.com. Thank you for your time.
All right. Thanks so much, Dan. So if you go to our website, saratech.com, and go over to events, just roll over it and you'll see the customer enablement series here. If you click on that, we're making it a lot easier for you this year. You no longer have to register for every single session. So what you'll do is you'll just click register here. And when you register, you have registered for the entire year. Just add them to your calendar, and then you can pick and choose which ones you'd like to go to based on your interest. Okay, have a great day.